I would like to welcome you to our first session today, and I will be your chair for this session. I'm Henrik Ruscher, and our first session is heat and mass transfer. And with no further ado, I would like to introduce our first speaker, Dr. Tom Weyer, and he will give a talk on convection in liquid metal batteries, comparing results from OpenFOAM, Semtex, and Sem months. I hope it's not going to be too explosive, and I'll hand over to him.
Hello, everybody. From my side, I try to share my slides. Okay. Does it work?
Yes, it does.
Okay. So welcome. Liquid metal batteries are something a bit unusual. They typically don't explode, but they are very hot, 450 centigrades. These are 3 layers of mutually immiscible liquids, basically a fused salt sandwiched between 2 molten metals. And the fused salt is a very important part of every battery. It's an ion conductor, and that's a very important part of every battery. Due to density, these 3 layers are in stable stratification. They are a bit corrosive, but during cycling, the pro is that we don't have structure degradation because lack of structure, so everything is fluid. Of anode and cathode, nothing can age too much. We have a fully liquid interior in these cells, and therefore fluid mechanics has a role to play here. When I refer to anode and cathode in the following, they are named by their role in discharge, as it is common convention. I focus on the system lithium bismuth. That means lithium on the top, bismuth on the bottom, and various salt mixtures in between. The voltage of the cell at rest, so the open circuit voltage or rest potential, it's simply proportional to the activity of lithium in the bismuth cathode. And I've taken here a diagram from Webner and Huggins, 1978. They measured that there is a relatively steep decrease of the open circuit voltage in the one-phase regime. On the right-hand side is the phase diagram. So as long as you're in one phase, the open circuit voltage decreases proportional to the negative logarithm of the activity of the lithium in the bismuth. And then when we come into the two-phase regime, we have a stable open circuit voltage of around 750 millivolts. To give you an example, we have cycled such cells in the lab for quite some time, and at the moment we are still around with relatively small cells. So if should they explode, it wouldn't be too dangerous, but they didn't, as I said. So if you discharge or charge a cell, it's not only the open circuit voltage that counts, but you also have to take care about voltage losses. And voltage losses are first and foremost the ohmic losses due to the resistivity of the electrolyte. And then we have several overvoltages, but most of the time only the overvoltage in the cathode due to mass transfer there plays a significant role, as well as I said already, the ohmic resistivity. During charge, it's basically charging means overcoming the resistivity of the electrolyte, and then there is nothing else. Basically, there is an offset voltage given by the electrical resistance of the electrolyte, and the reason behind this, we have very intense mixing during charge. I will come back to this a little later. But during discharge, things are different. there is not only the offset due to the ohmic losses in the electrolyte, but there are additional so-called overvoltages, and the main role here is played by diffusion. And the thing is that during charge, we start with a well-mixed lithium bismuth alloy, where we take away from the top low-density lithium. That means the remaining alloy is much denser, and it starts to sink down, and this solute convection is very intense and mixes the cathode very well. But during charge, it's the opposite. We deposit low-density lithium on the top. This is a stable situation, and mass transfer is basically only done by diffusion. And therefore, we have a relatively large diffusion overvoltage. And one aim of our investigations is to try to control this overvoltage and get rid of it, basically, because it means losses, energy losses in the end. Going back to the three layers, so we have a liquid metal on top, as I said, with a very good electrical conductivity, and with the good electrical conductivity goes a very good heat conductivity. Then the molten salt, much lower electrical conductivity, much lower heat conductivity, and on the bottom again, good electrical conductivity, good heat conductivity. That means the main heat source in the cell is the middle layer, the electrolyte. And if you do a static calculation without any flow, you end up with a profile like that is shown in the middle. So parabolic, basically, in the electrolyte, internally heated, and a very small voltage, temperature drop along the anode, and a little larger because of the less good thermal conductivity at the bottom. So this is a typical conductive temperature profile. And another thing I wanted to say here is that the height ratio of the anode and the cathode can be determined by the mole fraction at discharge. So if you remember the phase diagram, the one phase region stops at 0.4 lithium in the alloy. That would mean the anode is just half as high as the cathode. And if you go into the fully to lithium-3 bismuth, then the anode would be twice as high as the cathode. So a factor of 2 is the maximum meaningful. That's what I wanted to say. To the codes we used, of course, OpenFOAM. Our solver is based on Buzinesque pimple foam. I don't want to add much more on this because there's the next slide. Semtech is a spectral element code, solves the incompressible Navier-Stokes equations, and Femans is a mixed spectral and finite element code, and it solves the magnetohydrodynamics equations in 3D axisymmetric domains. For OpenFOAM, we used a parent-child technique to couple the mesh for temperature. That means a heat transfer equation that's solved in the full cell, and velocity, pressure, and concentration in the cathode are solved on child meshes in the respective layers only. There are some boundary conditions. When you look at the kinetic energy during charge, we have the solute convection in the cathode. The highest, by far highest, kinetic energy is in the cathode, then the electrolyte, and the lowest, as a rule of thumb, in the anode, except the case with an overheight anode. There we have also relatively high kinetic energy, but that's due simply to the larger Rayleigh number due to the height. Yeah, looking at the electrolyte, this is characterized by internally heated convection and viscous coupling. Viscous coupling is a momentum transfer from the cathode during charge to the electrolyte. That means at the lower boundary of the electrolyte, we have For a thin electrolyte, 5 millimeters thick only, there is the Rayleigh number is below the critical one for most current densities. And we have the most intense flow is directly at the boundary to the cathode. And the temperature profile is relatively regular vortex cells, or characterized by relatively regular vortex cells. Quite the opposite, if we switch to a thicker electrolyte, 10 millimeters, then this internally heated convection becomes dominant, and that's a classical picture from Kulaki and Goldstein. So we have a really asymmetric temperature profile on average and penetrative convection in the electrolyte. So there's really a change between two completely different regimes. And this can also be seen in the electrolyte Nusselt numbers at the top and bottom part. For the low Rayleigh number, viscosity or viscous coupling driven regime, the Nusselt numbers at the bottom boundary are higher than the Nusselt numbers at the top boundary. That's quite unusual. But switching to the thick electrolyte, we go back to normal, where the upper boundary Nusselt numbers are higher than the lower boundary Nusselt numbers. Yeah, some images done by Semtech. So on the left-hand side, you have a view from the top on the constant or the mass fraction of lithium distribution shortly after the onset of the instability. What you see are many on the right-hand side are just from view from below, and you see an isocontour of the mass fraction of or mass concentration of lithium colored by the vertical velocity. So you see a lot of small plumes after the onset of the instability, and they decay into larger structures after passing the maximum, and after passing the dip after the maximum, you gain smaller structures, but not as small at the beginning. This is just some impressions. And now for the comparison, that's the only slide I have on that. Basically, you see that the time dependence of the integral values by all three solvers for the same case are roughly the same in terms of velocity as well as mass concentration of lithium. To conclude, and that's my very personal view, so OpenFOAM gives you, as you all know, a lot of flexibility, can be easily extended, and it's very resilient. If you have to do something very fast, then I would suggest using Semtech if you can live with the possibilities it has to offer to its users. And then there is Svemans, which brings with it already a solver for the complete magnetohydrodynamics equations, which come in handy if you have more problems than just heat and mass transfer to solve. It's fast as well, and it's written in Fortran 90, so it's classic foundation. That's about it from my side.
Very good. Thank you very much. I will do the clapping for you for the moment. And I have two questions for you from the same author, from Holger Marshall. So he says, very nice talk. Shouldn't the Ernst-Planck-Poisson equations for the ionic species diffusion be solved within the non-dilute electrolyte?
Yes, that's completely correct. But it's it's really a difficult task for us. Up to now, we completely disregarded this aspect. I think by good reason. The mixing, the convective mixing in the electrolyte is relatively good. We don't measure any transfer resistivity there. So I think it's reasonable to abstract away from the very complex transport in ionic substances, but that's something that's on our agenda. We are already working on it, but it's not ready for presentation.
Okay, thank you very much. I have one more question. I have 3 more questions in the chat, so maybe you can answer them later. I will pick the one from Herbert Yasak. Excellent work. Did you consider stability of the free surfaces between the liquid phases?
Yes, we did so in the past. This plays, from my point of view, it plays more a role for larger cells, but there are specific aspects that Norbert Weber will discuss in his talk in the evening today, where he found things that are also important for small cells. Yes, stability of the interfaces is a very important question, and one should look for this as well.
Okay. And I have one more for you. I think that's a quick one from Kaspar Dacic. What were CPU times for 3D Semtex calculations? And maybe you can put that into perspective with OpenFOAM as well.
The calculation times?
Yes.
Have I got? So Semtex 3D. So all these calculations, they took a few days, and it depends on what you're looking for. So for Semtex, we use 12 days on 32 CPUs.
Mm-hmm. And the comparable OpenFOAM, because you said that OpenFOAM.
Yeah, the thing is that we have not managed to, or we haven't used OpenFOAM for the 3D. OpenFOAM is yeah, I would say roughly 1 order of magnitude slower, but it's not a fair comparison, because Semtex is very specialized, and it allows only to have only one scalar transport. For instance, if you can live with this, you can use the speed, but if you need more, then it's not easy to change.
Yeah, it's also completely different numerics, but
right.
I just wanted to put the question forward to you. There is one more question in the chat, so if you could answer that offline or
yeah,
that would be very nice of you. And I would like to move on. Thank you very much for your talk.
Thanks for the question.
Our next speaker is Dany Drehlen, and he will discuss magnetothermal hydrodynamics of low temperature plasmas for advanced manufacturing applications. So the floor is yours, Drehlen.
Hi, so can you hear me? And can you see this?
Hear you well.
Sorry, is this the?
And we can see your slide.
Yeah. So can you see this yet? So I think the title was a little bit wrong. Maybe you were thinking of a different talk, but my title of my presentation is mesoscale solidification models for additive manufacturing processes. Sorry. So I'm sure most of you are aware of additive manufacturing, commonly referred to as 3D printing, but I'll give a very brief overview. So unlike traditional manufacturing techniques, the part is built layer by layer by spreading a fine layer of metal powder and selectively melting it with a high energy heat source such as an electron beam or a laser. So once the raster scan for a given layer is completed, the build plate is lowered and the powder is spread evenly across it, and the process is repeated. So additive manufacturing boasts many advantages over conventional subtractive methods. So for one, far more intricate and efficient structures can be produced, which can be tailor-made to a specific application, and it also allows for the use of just a single part, where traditional techniques might require several parts with many manufacturing steps. So the modeling approach that I use is inspired by cellular automata. So before I get stuck in, I thought I'd just introduce cellular automata with a classic example, which is Conway's game of life. So cells can exist in only one of a discrete number of states, being dead or alive. And cells can either die by overpopulation, loneliness, or they can be reproduced if they have exactly 3 live neighbors. So although the rules are very simple at the local scale, global complexity can emerge once we zoom out. So my model for solidification takes inspiration from these cellular automata. So the discrete states would naturally be solid or liquid, but we define a single layer of interface cells so that growth can be modeled continuously. So the advantage of discrete states here is the growth is only calculated for interface cells, which typically make up a very small fraction of the total number of cells in the domain. So again, the rules or the construction of the model is relatively simple at the local scale, but complexity emerges once we zoom out from the competitive growth of a large number of individual grains. My model is based on the classic decentered square algorithm developed by Gandin and Rapaz in the 1990s. So it takes advantage of the fact that cubic crystals grow approximately as squares in 2D or octahedra in 3D. And so each interface cell has an octahedron associated with it. This will grow due to the undercooling, and once it engulfs a neighboring cell center, it switches this cell to interface and initiates a new octahedron. So the center of the octahedron typically doesn't coincide with the cell center, and the starting length is non-zero. So the size and center of the octahedron is determined by the specifics of the algorithm, but one corner of the octahedron coincides with the corner which captured it. So the growth velocity of these corners is modeled to be dependent only on the thermal undercooling, which is the temperature difference below the liquidus. And I use the KGT dendrite tip kinetics law to obtain a curve-fitted polynomial for a relationship between growth velocity and the thermal undercooling. So to implement this in OpenFOAM, I create a custom class called CA-cell for each cellular automaton. So among other things, it stores the state of the cell, so 0 being liquid, 1 being interface, and 2 being solid. And also the details of the square or octahedron being the center, the size, which is defined as the half diagonal length. So originally I checked whether an octahedron had captured a neighboring cell by using mesh.findCell, but this was extremely slow as it needed to do a full mesh search hundreds or even thousands of times per time step. So instead, when I initiate a square or an octahedron, I calculate the length that the half diagonal needs to be in order to capture each of the neighbors. So this sped up the algorithm by over 2 orders of magnitude and was definitely worth doing. So the entire cellular automata algorithm lives as a list of these CA cells, one for each cell in the mesh. So for every time step, I loop through the entire list and only consider interface cells. So I calculate the growth velocity from the KGT model based on the temperature field. I then globally adjust the time step such that growth velocity doesn't span more than 20% of a cell in time step. I then loop through all of the cells again and increment the half diagonal length based on this growth velocity and the time step. And then I check if the length has exceeded any of the capture lengths for each of the neighbors. So this is extremely cheap to compute compared to mesh.findCell. So that's definitely something to keep into consideration if you're planning on implementing it yourself. So then for any cells that are to be captured, I cycle through those and basically capture them. So they inherit the crystallographic orientation from the parent octahedron. So I set the state to 1 and then calculate the square center and the starting length based on the specifics of the algorithm. And I calculate the length needed to capture each of the neighboring cells. So once an interface cell no longer has at least one liquid neighbor, its growth can be ignored by switching its state to 0, or state to 2, sorry. So here I show some of my earliest results after implementing the algorithm in 2D. So the case is isothermally cooling with 20 grains nucleated with random location and random orientation. So you can see that as grains meet, there's no grain overlap and growth stops. So to extend the capabilities of the model by allowing it to be coupled to more advanced thermal models, which are being developed by some of my colleagues, reading of temperature histories from an existing OpenFOAM case is supported. So at the start of the simulation, I read all of the possible time directories from the OpenFOAM case. Then inside the runtime loop, I create, I basically read the current temperature field and read the next temperature field. And so this is so that I can interpolate linearly between them to avoid step jumps or any discontinuities. So an important step here is I only interpolate for cells that could possibly change state. So that's liquid cells they will go below the liquidus temperature by the next time step, or solid cells that won't be melted by the next time step. So this again sped the algorithm up by at least an order of magnitude, if not more, because most of the cells are essentially ignored. So to further boost the speed of the algorithm, I use OpenMP parallelization. So this is different to MPI, which is what OpenFOAM uses predominantly, as each thread has access to the same shared memory. So OMP is based on OpenMP is based on a fork and join model. So the program starts in serial, and then when we encounter a region where it's very computationally intensive, we can split it into parallel, so we can spread the work across multiple threads, and then we can rejoin to run the rest of the program on the master thread. So here I show a case setup for a single pass of a laser over a solid substrate for an additive manufacturing process. So the laser heat source is modeled to have a Gaussian distribution of intensity around the spot center, and is applied as a volumetric heat source to the cells at the top of the domain. So I create a custom boundary condition for convection and radiation, and this is applied to all surfaces except for the bottom, which is held at a fixed temperature. So the starting microstructure was generated in Dream 3D, which is a free software package that can be used to generate synthetic microstructures or reconstruct EBSD images. So the material is aluminium 4% copper, assumed to have a Gulliver-Scheil liquid fraction relationship with respect to temperature, and the growth kinetics are obtained from my KGT model, which I presented earlier. So if we look at the animation, we can see the path of the laser. So once it reaches the end of the path, the power is switched off and the material is allowed to resolidify. So on the left, I show results in 3D with any cells that were melted at any stage being highlighted so that the melt pool can be easily identified. And at the top, I show a narrow slice along the center of the beam. So as you can see, a columnar microstructure develops and tends to be aligned with the local direction of heat flow during solidification. So here are some close-ups of the results, which I think agree well qualitatively with EBSD images seen in the literature. So this EBSD micrograph is for an aluminium silicon alloy, whereas my simulation is for an aluminium copper alloy. But it does give me some confidence that the results are at least in the right ballpark. And if we look at the bottom figure, we can see that the columnar grains tend to be aligned with the local direction during heat flow. So that concludes my presentation for today. Thanks for your attention, and I hope you found it interesting. Here's my contact information if you'd like to contact me, or if you have any further questions. So I've tried to leave some time for questions. Thank you.
Thank you very much. So here we go. You get some clapping. Did you hear that?
Yeah, thank you for that.
Okay, perfect. Just making my way through the portal here. I have a number of questions for you, and I'll pick the one from Ken Wardle. Did you compare the speed up of choosing OpenMP versus just leveraging the existing MPI implementations?
Well, I think I forgot to mention it, but so if we look at this, basically the interface cells are very confined to only, so if I was to use MPI, the interface cells would be confined to only maybe 1 or 2 blocks at a time, maybe 4 blocks at a time. So most of the blocks would be sitting idle. So I didn't actually try to implement it in MPI because I thought that OpenMP would be more suitable. Yeah, so.
You're solving a load balancing problem at the same time, I would say.
Yeah, exactly, yeah.
Yeah, okay. And I have another one from Lila Koloja. Very interesting approach, thank you. can you use different growth kinetics to model different crystal growth in metal solidification? Can you handle somehow mushy zones?
Yeah, exactly. So the growth kinetics are generated like specifically for a given alloy. So sorry, I'm not sure which slide it is. Yeah, but the growth kinetics are generated specifically for a given alloy. So if I change the alloy properties, I'll obtain a different growth law polynomial. In terms of handling a mushy zone, see, my models are considered to be an envelope-based model, so I track the edge of the grain boundary and don't necessarily care about the detail inside the grain. So whilst inside the grain boundary, it would be mushy, I don't really consider that. So these models are an envelope-based approach rather than a more micro-scale model like a phase field, for instance, which would track specifically the mushy zone.
Okay, thank you very much. I think we have to leave it. There is one more question from Holger, so I'll leave that to you for answering that on the portal. Okay. I'm sorry for mis-advertising your talk. So our next,
no problem. Okay.
Our next speaker is Dr. Tom Flint of the University of Manchester, and he will talk about magnetothermal hydrodynamics of low temperature plasmas for advanced manufacturing applications. The floor is yours.
Hi, everyone. So can I just check that everyone can see my slides okay?
Perfect.
Brill. Okay, great. So yeah, first of all, I'd like to say thank you very much for having me. It's really, yeah, a massive honour to be talking at this workshop, especially seeing as I can see some of the attendees, some of the real heavyweights of the community. So it's yeah, really great to be here. So thank you very much. So I'm going to be talking about this sort of new magnetohydrodynamics framework that we've developed at Manchester with applications to basically to dissimilar domains, so things where you have an interface with the difference in electrical conductivity. So myself and Dr. Pratik Shantra, just sort of we're the people that did, you know, sort of derived the framework, and I implemented it in OpenFOAM. So so first of all, I guess it's worth saying why we bothered about modeling these advanced manufacturing processes. And we've had a really great talk just then about microstructure development, so I'll not spend too much time on that. But basically, when you apply a really concentrated thermal load into a metallic substrate, you generate really large stresses. And in a metallic structure that's welded, generally the part will fail at those welded joints. In those welded joints, so what you can see here is a fracture near to a weld, and these sort of really heterogeneous microstructures being generated due to sort of these high density heat inputs. So that's maybe not so important in a lot of situations. Maybe you can just replace the part. Obviously that comes with a sort of economic cost, but in applications like nuclear power plants, nuclear fission, nuclear fusion power plants, you need your structure to survive a very long time, because it will probably get irradiated. So you don't want to be having to replace things. So, you know, we need these things to last for sort of decades, multiple decades. So we need to understand how the microstructure and how the stresses develop, so that we can predict how that part will behave in its lifetime. So generally the sort of cutting edge modeling approaches for how, you know, the heat profile evolves in the substrate is a thermal fluid dynamics approach, where you would solve a momentum transport equation, heat transport equation, species transport equation, or just, you know, not like a volume of fluid type approach, like interfoam type approach for the metal and the gas. And then you'd apply a volumetric heat source, or you'd apply a surface heat source. But the problem is, with those surface heat sources, you have to fit them to the sort of experimentally measured or experimentally applied heat sources. So that's sort of a bit of a bottleneck. So what we were trying to think of was, how can we better physically capture that heat source? And if you want to do that, well, the heating of the substrate is due to Joule heating, so the resistive heating of the electric current passing through the gas phase and the metal phase. So if you want to understand that heating and put that heating term into your heat transport equation, you need some description of that current density evolution, if you like, in the domain. So yeah, so these are the governing equations, I guess. So we've got an energy transport equation in red here. So this J squared over sigma E. So sigma E is the electrical conductivity. And that, yeah, so this is the Joule heating term we're interested in. I'll not spend too much time on the sort of peripheral terms, but we've got latent heat here as well. And we also want to solve this momentum transport equation, sort of should obviously be really familiar to everyone here, I guess. But the key thing is we've got this Lorentz force that couples the magnetic field to this momentum equation. And then also we have this like species transport equation for the kth phase species, so volume fraction transport equation. I made a mistake actually in my abstract. I think I called it mass fraction, but it's like, yeah, obviously it's volume fraction. So so yeah, so what we've done is we've derived this new, sorry, I should say that the limitation in the literature is that all magnetohydrodynamics, the magnetic induction equation that we need to derive something for J, the current density, which is what we're really interested in, they're derived for constant electrical conductivity. So what we've done is we've said, well, let's assume that magnetic permeability, but let's assume that electrical conductivity isn't constant. So can we derive the magnetohydrodynamics equations to account for that gradient in electrical conductivity? So we take so for non-relativistic speeds, this d by dt, I think it's charge density, goes to 0. So J is the curl of the magnetic flux density divided by the magnetic permeability. Well, if magnetic permeability is constant, then that comes outside the difference operator, obviously. So we derive this by then taking the curl of J for the two expressions we have for the current density, and then we can use this vector identity here to get to this to get to this new magnetic induction equation where the electrical conductivity sigma is now not constant, it's a function of position. So and also just I should note that this, you might think, well I was interested anyway, that in MHD foam, which is sort of the OpenFOAM magnetohydrodynamics code, we're missing this, it's missing this, I think it's the grad B transpose term. That's because if your electrical conductivity is constant as well, then you can take both of those terms outside the difference operator. So when you take the curl of these terms, there's a much easier vector identity. So we curl of B is the gradient of the no magnetic monopoles. So then we just have this Laplacian term, and that's in MHD foam. So that's, yeah, just to say that's why, I guess that's why MHD foams doesn't have this term. So yeah, this is just sort of an explicit proof, because sometimes you have to be careful, because some of these vector identities don't actually hold if one of the operator one of the vector fields is a difference operator. So I just went through and just showed that actually it's the vector identity I used does hold. Actually, you get the same result if you use the vector identity or explicitly go through all the terms. So, and then this is just the solution algorithm. So the PDEs are solved semi-implicitly each time step. So the first step is to solve the pressure velocity coupling, which is using the piezo algorithm. So yeah, we iterate over the velocity and the pressure to get to convergence, and then we solve this magnetic field problem with this fictitious magnetic pressure. It's the exact same approach as in MHD foam. I guess the only caveat is that I tried a few different, so MHD foam and the code how I've implemented this in OpenFOAM uses the projection method to project the computed magnetic field onto a divergence-free magnetic field, similar to how IcoFoam and the incompressible flow solvers work. So I tried a few different. There are a few different schemes to do that. So I think it's called the 5-wave scheme, or you can to take the product of any divergence, non-zero divergence, and apply a fictitious velocity to advect the divergence of the magnetic field outside of the domain. But I think I'll talk about that later. So maybe the next thing to say is that we validated it, obviously, which is obviously quite a good thing to do. So we used the Hartmann flow problem. I've not exactly checked, but I think the solution that you get by including this gradient of the magnetic field transpose term is actually slightly better than the MHD foam. I can't say for definite, but so we've applied different magnetic field strengths transverse to the flow, and we use this solver, but this is obviously just for a single phase, so just including that extra term, and there aren't any analytical solutions for a multi-phase, not that I know of anyway, so please correct me if I'm wrong. So one of the things we'd like to do next is look at some sort of these plasma jet scenarios and apply our approach to that, and just double check it predicts experimental results. So yeah, we're quite happy with validation. So then I'll better move on because I've run out of time. But so then we apply it to what we were interested in the first place, an arc welding scenario. So this is arc welding of an aluminium substrate. So I've taken the iso contour of the aluminium volume fraction, so at 0.5. So yeah, I've coloured the electrode in magenta. So I'm not sure if you can see, but the magnetic field is applied as a bound condition at the electrode. Then that Joule heating term initiates a really intense local heating at the electrode, and also initiates this Lorentz force that depresses the weld pool, and as time progresses the size of the weld pool increases, and due to Marangoni convection, which is, for those that don't know, is the temperature dependence of the surface tension coefficient, due to that we get sort of a wider and shallower weld pool. So I've just sort of zoomed in on one of those figures here, just so you can see this sort of vortical magnetic field, which is the stream tracer lines, and the glyphs here are the velocity field. So you can see that yeah, going through the domain really. I think that's everything to say on that. So yeah, the other thing to check, yeah, just this solenoidal constraint. So I've seen in the literature, and even there was an OpenFOAM a presentation I saw on it where people don't double check that, or don't force the magnetic field to be solenoidal, so to be divergence free. So as I said, we tried some different approaches. We actually found that the projection method used in MHD foam and in the solver we've written is the preferred method. Actually, it's much more robust, and it allows you to get a much smaller magnitude magnetic field divergence. So yeah, as I say, we tried these different approaches, and the projection method definitely was the preferred method. So yeah, really happy with that. So for the future work, actually we over predict the heating, because the electrical conductivity in the argon phase, the gas phase, is really strongly temperature dependent. So as you increase your temperature, your conductivity actually decreases by sort of 4 orders of magnitude. So that, if you remember, the Joule heating term was J squared divided by the electrical conductivity. So as you get to the sort of temperatures that the plasma does reach, the electrical conductivity, if it's 4 orders of magnitude higher, that Joule heating term will be 4 orders of magnitude less, obviously. So something we'd like to do is add some sort of lookup table functionality to the solver to incorporate that. And then we'd like to release the solver. We plan to release the solver probably when we've implemented this, or maybe before. We're not really too fussed about that, but that's another thing we'd like to do. So if you are interested, then just keep your eyes peeled, or drop me an email to see when it's ready, or I can send a preliminary version over shortly. So and yeah, so that's my talk. So thank you very much. Sorry I went over slightly, but this is me. So if you'd like to ask any questions, that's my email address, and my colleague Dr. Pratik Chantraj would also sort of be, both can answer questions. So yeah, thank you very much.
Thank you very much for your talk. So you also get some look and feel for the live audience. And
yeah.
I have 2 questions for you, and I'll take one, the one that was first from Federico Municini. Thanks for the presentation. How do you model the solid melting in the arc welding? What thermophysical models are you using for transport properties of the plasma? Okay, yeah, great. It's like the enthalpy porosity method for the melting of the substrate. So yeah, it's like the details of it are just when you solve the temperature equation, you sort of iterate over the volume fraction to make sure you get the latent heat of fusion correct. So that's yeah, that's how we solve for the melting. And also maybe I should say then there's the Darcy source term in the momentum equation. So when the substrate is solid, there's a really high magnitude source term there to force the velocity to be zero basically. And then the second part was the thermal. So we just assume at the moment, we just assume constant thermophysical properties in each phase. So yeah, so the mixture thermophysical properties are a weighted sum of the volume fraction of each phase and the particular property of that phase. So viscosity, density, yeah. So that's how we model the mixture thermophysical properties. Wonderful. Thank you very much. We have 3 more questions, so please attend to the chat and answer them there. Yeah, sure. Yeah, great. Thank you. Okay. Thank you very much for your talk. Thank you. Thank you, everyone. So our next speaker is Dr. Mirko Magnini from the University of Nottingham.
Yes. Can you hear me?
Yes, I can hear you well. And his talk will be on direct numerical simulations of boiling flows in microchannels.
Okay. You see my screen, everything is all right?
Perfect, it's moving.
Thank you. Thank you, Chair, for your introduction. I'm very pleased to be here and present this work in this occasion, work that I'm developing together with collaborators at the University of Nottingham. We're talking about direct numerical simulations of boiling flows in microchannels. And the application we have in mind for this is the cooling of computer microprocessors. If we look at this graph here, we see that this graph shows the trends in the past 50 years of a few parameters characterizing microprocessors. In particular, we can see that the typical power, so this is the thermal design power, the thermal power generated by the microprocessor is now between 100 and 1,000 watt. And if we take, for example, a modern workstation that, for example, one of my colleagues is using, we take the thermal design power of 280 watt divided by the die size, the size of the CPU, we get quite large heat fluxes on the order of megawatts per square meter. Now, the advantage of using two-phase flows, and in particular of using boiling for the thermal management, we see here an example where the fluid boils while it's flowing within a multi-microchannel evaporator, which is placed in direct contact using a dielectric fluid with the CPU to be cooled down. And the two-phase flows, they have the advantage of, obviously, because you dissipate the latent heat, you get a very large heat removal on the order of what is required by modern and future CPUs. It guarantees uniform surface temperature because the fluid is supposed to stay about at the saturation temperature while boiling. And the two-phase flow, they have a positive response to hot spots. If there are zones of the CPU where the heat flux is increased, then the two-phase flow should be capable of reacting by removing more heat. Now, two-phase flow, they have two-phase flow patterns. We see here some videos where we see the development of bubbly, slug, and annular flow. And what are the key ingredients for simulations if we want to capture, in particular, a slug flow, the one in between, which is the one that we are focusing on? What do we need for this? We need a very accurate surface tension, and we will see why. And of course, we need a phase change model to capture the boiling component. Now, let's start focusing with the adiabatic flows. So let's just take a look at the case without phase change. We are now evaluating the performances of a geometric volume of fluid method implemented in OpenFOAM. In particular, a special library that has been released recently by Scheffler and Roenby. I'm missing the reference here, but it's going to be there in the next slides. We are solving the incompressible flow equations for the volume of fluid model. And the surface tension force is calculated by taking the curvature based on a parabolic reconstruction of the interface profile. As I will show you, the curvature is very important in this kind of flows. At least the surface tension force is a very important force. This is the range of capillary Weber numbers that we are studying and the aspect ratio of the channel that we are studying in the case of adiabatic flows. Now, why is it so important to capture well the surface tension force? The standard interFOAM solver, the Moore's algorithm, calculates the curvature based on derivatives of the volume fraction, which is a discontinuous function across the interface. Curvatures are not very accurate. What you see is the development of these so-called spurious velocities at the interface. So we have done a test of the interFOAM isod vector and some other more special geometrical calculations of the curvature that are available in the Twophase flow solver that is being released by Scheffler and Roenby. And you see that, for example, isod vector gives the worst performances in this kind of test case. interFOAM is a bit better because the interface is more diffused. But then if you really want to reduce the spurious current, you need to implement geometric reconstructions of the curvature, for example, reconstructed distance function, parabolic fit, which is the one we are using for the adiabatic study, or height function algorithm. These are all implemented in Twophase flow solver by Scheffler and Roenby. Now, when we look at the flow of bubble in, as example, in a circular channel, which is a simplified model of what we want to study, there is available theory from Bretherton and Taylor that shows how the streamlines should look like ahead the bubble nose. And for example, this is what you get with interFOAM at relatively low capillary numbers. You see on the front of the bubble, you have all these sort of strange recirculation patterns very near the interface. And within the bubble also, you have some weird velocities appearing. While in the same conditions, same mesh, same time step, same everything, using the geometric VOF of isod vector plus applicar RDF to calculate the interface, the fluxes across the interface, and curvature in the surface tension force using the fit paraboloid method, you see that we get streamlines that they look much more how they should look. We don't see anymore any weird velocity field around the interface. Now we have validated because we want to study boiling in microchannels. So we validated the flow of long bubbles in the adiabatic case against numerical simulations that were performed by Delozar et al. Using a finite element interface fitting method. So in this figure here, we are looking at the radius. So we take a bubble flowing across a channel. We take the terminal steady state situation in which the bubble translates with a constant speed, and we take a cross section along the bubble. What we are measuring here in this cross section is the width of the bubble rescaled by the channel width. So in the top left figure here, you see a sample image of the cross-section with the blue being the bubble and the gray being the liquid. In the figure in the bottom here, we see the bubble width rescaled by the channel width, so maximum can be 1, as a function of the capillary number evaluated based on the bubble speed for 4 different values of the aspect ratio. Aspect ratio 1 is the square channel, aspect ratio 2, 4, 8 are the rectangular channels. We see that there is a very good match between the numerical simulations run with isod vector plus fit paraboloid and the benchmark case. We see that, very generally speaking, from aspect ratio 1 to aspect ratio 2, 4, and 8, we see that as we see in the graph, the bubble width rescaled by the channel width is decreasing. I have much more result than this, but I don't want to focus on this part here. I prefer to move forward now to the boiling case. What we're doing now for the adiabatic flow is to study more into detail the film thickness all around the bubble as a function of the properties. Now, yeah, I forgot I have also this slide where I compare the fit paraboloid with interFOAM, the empty symbols. We are not doing this for all the cases, but for a few of them. We see that for the square channel, the simulations are more or less the same, but as the channel becomes more flattened, it seems that the paraboloid fit captures better the benchmark results. So it seems to perform a bit better than interFOAM. Now, for what concerns the boiling, we are using interFOAM, to which we implemented a phase change based on Hart and Vondra model. So it's an incompressible flow model where we have source terms related to phase change on the volume fraction equation, momentum equation, and energy equation. We see here in this video an example of a typical benchmark case where we have a spherical bubble growing in superheated liquid. So we have validated the solver with the benchmark simulations with the theoretical solution for this case. What we have done afterwards has been to start one simulation of one bubble boiling in a microchannel. So we have a microchannel, we have a validation with experiment from Mukherjee et al. A microchannel of 0.2 millimeter of hydraulic diameter square. We initialize a tiny bubble at the center, we let it grow because of boiling. Heat is provided from the bottom of the channel, and we compare the bubble growth versus time with the experiments, and we see a very good comparison. So what we are doing now, funded by a national grant, is a comparison with experiments that will be run at Brunel University, London. Here we see an example of a simulation of a boiling case using their setup, their conditions in which we see the bubble growing, the effect in cooling down the wall, and on the figure here, we see the dry patches generated by the evaporation of the liquid and the localized source term due to evaporation around the contact line. This is ongoing study, so it's a bit qualitative what I'm showing on this. We also have dynamic mesh refinement, even though it's without load balancing. So we see a serious deterioration of the performances as the bubble grows and moves along and the processors are no longer balanced. So I leave you here with my slides about conclusions. I think I've run out of time, and I thank you very much for your attention.
Thank you very much. And here comes your applause. I think we have time for one question or maybe two, we'll see. The question I have for you is from Kent Waddle. Did you compare mass conservation between Plick options and interFOAM? How do you deal with mass loss in the Plick algorithm?
Well, we check the volume of the bubble along the simulation. The volume of the bubble, I mean, integrating the volume fraction all throughout the domain. And I don't have on the top of my mind the exact values, but I remember that the change in the mass of the bubble was below 0.1% throughout the simulation. So they were both very robust on that sense.
Okay. And I think I have a very quick one for you from Milad Bagheri. Hi, thank you for your talk. Why does the performance, and I think he means parallel performance, drops when you're using dynamic mesh, RK refinement, dynamic refinement?
Well, the problem is that just a few of the processors, they get many cells. Like in this case here, the bubble is still, let's say, in processor number 1, and processor number 1 gets a load more cells all of a sudden. And that becomes the bottleneck of the entire simulation.
Yes, you're refining around the interface, and the interface is moving, right?
Exactly. I'm refining only around the interface, and the interface is moving. That's the problem.
Okay, thank you.
Thank you.
Thank you for your talk. Okay, so I'll use the time. So this is in a good tradition of OpenFOAM, of the workshop. This is not just about listening to presentations. So please use the infrastructure that is provided to you to make contacts and meet people. I don't know what the speed dating is going to be like, but I'm about to try and find out. There's also the whiskey tasting. So use all the features that are provided to you to make contacts. It's I know it's difficult and much better if we were all meeting in Dublin, but we have to make the best out of it. So thank you very much for attending this session, and thank you very much for the speakers again. I'll make this as a collective clapping, and see you at the other sessions. Thank you very much for attending. Bye-bye.